Now we will draw the capacitance curve for MOS capacitor. If we apply a negative gate voltage, then will operate in depletion mode, and in the depletion mode the capacitance is C oxide. When we apply positive gate voltage but less than threshold voltage Vt, the capacitance will be the series combination of two capacitances and it goes on decreasing as the voltage increases. When the voltage Vt is crossed, the capacitance again becomes oxide capacitance, C oxide. This is the capacitance curve. The maximum capacitance is C oxide and this is the minimum capacitance. This minimum capacitance will be C equal to 1 upon C oxide plus 1 upon CD minimum, and CD minimum will be equal to epsilon naught into epsilon silicon divided by XD maximum. So we can get this C minimum capacitance. This region will belong to depletion mode and this region will belong to inversion. Now in most capacitors, if the frequency of gate voltage Vg is very high, then in that case inversion layer could not form. Inversion inversion layer could not form. If inversion layer cannot form, then the capacitance in inversion mode also remain at its minimum value. This is the capacitance for high frequency and this is the capacitance for low frequency. This is all about MOS capacitance.
Depletion type MOSFET. The structure will be like MOS capacitor. And this P-type substrate will diffuse to N-type material, which will be acting as source and drain terminals. And this would be SiO2 layer, and this is for contact. This N-type material will be the source terminal of this MOSFET, and this N-type material will be the drain terminal of this MOSFET, and a metal plate will be there which will act as gate terminal for this MOSFET. This is metal plate, or for P type substrate it will be P plus polycrystalline silicon. If this is N substrate, then this metal plate will be N plus polycrystalline silicon. So this is basic structure of depletion type MOSFET, and during fabrication between source and drain terminals, a channel which will be N type region will be diffused during fabrication. So it will be a diffused channel. As this is P type material, this is N type material, this is N type material, P type, N type, P type. So there will be a depletion layer here, depletion layer. This is the structure for depletion type MOSFET. Now we will see the operation when proper biasing is provided to depletion type MOSFET. Now we will provide biasing to the to this MOSFET. This is N channel, N plus material source, N plus material drain, and this P type substrate will be kept at ground potential. Now we will apply some potential between source and drain terminals. This source is an N type material, and we will keep this gate negative with respect to source. So this voltage would be our gate to source voltage, VGS, and a potential will be applied between source and drain terminals. This battery will be VDD, and the potential between these two terminal will be VDS, drain to source voltage. Now like JFET, we will draw first its transfer characteristics. In the transfer characteristics, we will draw drain current ID against gate to source voltage VGS. keeping VDS constant. Now as VGS is negative, the curve will be again in this quadrant. On this axis we will plot drain current ID, and on this axis we will plot VGS. Now as VGS equal to 0 volt, first case, if VGS equal to 0 volt, then for this VGS equal to 0 volt, this voltage between source and gate terminal will be 0, and as this is n-type material, in this n-type material there will be electrons, and these electrons will flow under the effect of electric field which is developed by this voltage VDS. This electric field will help these charge carriers to move in this direction and will contribute a drain current ID. So when VGS equal to 0 volt, in this channel the maximum number of electrons will be flowing in this direction, and they will contribute a current, drain current ID. When VGS equal to 0 volt, maximum number of electrons will be moving and drain current ID will be maximum, that is IDSS. Now we will increase VGS. Negative VGS is applied. With increase in VGS, as we saw in as we saw in MOS capacitor, when negative voltage is applied, the holes in p-type substrate will be attracted in the channel. Holes will be attracted in the channel, and due to these holes there will be a possibility of these electron and this hole, recombination of these electron and hole. Due to the recombination, the charge carrier concentration, the electron concentration in the channel will be decreased. So due to negative VGS, holes will be attracted in the channel, and due to recombination of electrons with holes, the net charge carrier concentration, that is electron concentration in the channel, will decrease, and hence drain current ID will decrease. For a large negative voltage VGS, many holes will come in the channel, and due to large number of recombination, the electron concentration will reduce to 0 and the drain current ID will reduce to 0. This voltage at which drain current ID reduces to 0 is called VGS cutoff or pinch off voltage, VP. So these are the transfer characteristics of depletion type MOSFET. Like JFET, these transfer characteristics have maximum current at VGS equal to 0 volt and minimum current at VGS equal to VGS cutoff. In this graph, we have seen that with increase in VGS, the drain current ID decreases, means the channel is depleted of the majority charge carriers electron concentration. So we will call this mode as depletion mode. So in depletion mode, the drain current ID decreases with applied VGS. So this MOSFET is said to be operated in depletion mode. This MOSFET is said to be operated in depletion mode. Now we will see enhancement mode. So in depletion mode, we applied a negative VGS. Opposite to this, in enhancement mode, we will apply a positive gate to source voltage. So we will change this battery. This time we will apply a positive VGS. Now remember again the MOS capacitor. In the MOS capacitor, when we applied a positive gate to source voltage or positive gate voltage, then up to certain value of positive voltage, the charge carrier concentration in the channel will be same. And for large positive voltage, large number of electrons from p type substrate will be attracted in the channel, and these electrons will form inversion layer. So the transfer characteristics for enhancement mode, this is for depletion mode, and these will be for enhancement mode. The difference between these two modes, that in this depletion mode we will apply negative VGS, and in enhancement mode we will apply positive VGS. So when VGS equal to 0 volt, again the maximum, the charge carrier concentration will be same as it was in the case of depletion mode. So same number of charge carriers will be moving from source to drain, and a drain current ID, in the last case we called it as IDSS, and in this case it will again be called as IDSS. Now in the last case we applied negative VGS. Due to this negative voltage, the electron concentration in the channel decreases. But in this case we are applying a positive voltage, positive gate to source voltage. So due to this positive gate to source voltage, the electron concentration in this channel will be increasing. So when we apply positive voltage, this is for depletion mode. For enhancement mode, if VGS equal to 0 volt, then we know that with positive VGS more number of electrons will be coming in the channel. So we will say that when VGS equal to 0 volt, minimum number of charge carriers will be moving from source to drain, and drain current ID will be minimum, that is IDSS. Now second case, when we apply positive VGS, when we apply positive VGS, with this positive VGS, the electrons in p-type substrate will be attracting into the channel, but these electrons will be attracted only if this applied VGS is either greater than or equal to threshold voltage VT. So when applied VGS is less than threshold voltage VT, the drain current ID will be almost the same, that is IDSS, means no electrons in p-type substrate will be attracted. So when applied VGS is greater than threshold voltage VT, these electrons in p-type substrate will be attracted in the channel. So the electron concentration in the channel will be increased, and drain current ID will increase, and we will get characteristics like this. So these are the transfer characteristics of a depletion MOSFET in enhancement mode. In enhancement mode we applied positive VGS, while in depletion mode we applied negative VGS. So as this MOSFET is operating in two different modes, we will have two equations. When it is operating in depletion mode, the drain current ID is equal to IDSS into 1 minus VGS upon VP whole square. Like JFET, this will be the current equation when it is operating in depletion mode. And when it is operating in enhancement mode, when this MOSFET is operating in enhancement mode, the drain current ID will be equal to IDSS into 1 minus VGS upon VT threshold voltage whole square. These will be the two drain currents for depletion mode and enhancement mode. This depletion type MOSFET is not important from the examination point of view. So we will directly draw the drain characteristics for this MOSFET. Like JFET, this drain characteristics will be uh, as we saw in the case of JFET. This will be the linear region or ohmic region, and this will be saturation region. We will get this curve for VGS equal to 0 volt. If we apply negative VGS like JFET, we will get curve below this, VGS equal to -2 volt. If we further increase negative VGS, we will get this curve for VGS equal to -4 volt. These curves will belong to depletion mode. Now if we apply positive VGS, the drain characteristics will be above this curve. This will be for VGS equal to 2 volt, positive 2 volt, and if we further increase the gate to source voltage, sorry, gate to source, positive gate to source voltage, VGS will be equal to plus 4 volt. So these curves will belong to enhancement mode. These are the drain characteristics for depletion MOSFET. The depletion MOSFET is not important from examination point of view, gate examination point of view. We will focus more on